So NeRFs are trying to solve the problem of view synthesis. That is, we're trying to generate new views of a 3D scene, given already we have a set of views of a particular scene. So as you can see here, NeRFs are taking several inputs of the same scene, but from different views. And they're finally trying to render new views that are not already present inside the original input of the same scene itself. So the nerves learn a specific neural representation for a particular scene. And for this is only for one particular scene. And for new scenes, we need to keep retraining nerves so that we can use them for other scenes as well. This is an example of a scene that is generated by a nerve. And this is also an example of a scene that is generated by nerve. So I'll like to talk about other machine learning models which are also trying to solve the same problem of view synthesis, just like nerves. One example is SRNs, which are called scene representation networks. So the way these machine learning models work is they take two inputs, the implicit and explicit camera matrices. Um, the implicit and explicit camera matrices can be denoted like this. So the first, on the left-hand side, you can see the implicit representation, which consists of a rotation and a translation vector. And this mainly is used to convert the world coordinates into the camera coordinates. And then after that, we would convert the camera coordinates into pixel coordinates by using the matrix on the right. So this was the input of an SRN. And so the output of an SRN is the RGB image, which denotes the scene from a specified viewpoint. So we can compare nerves versus SRNs in this video. So these are two particular scenes which have been generated by nerves and SRNs respectively. The left is generated by SRNs and the right is generated by nerves. So you can see in this case that SRNs cannot show high frequency details. For example, this is really blurry on this side, whereas nerves can easily show high frequency details, and nerves outperform SRNs in this case. Um, so if you want to compare SRNs versus nerves, uh, SRNs use something called occupancy values, whereas nerves use something called volume density. And volume density refers to how much volume, volume density refers to the amount of volume or matter present at a particular location. And the another main difference between SRNs and nerves is that SRNs can generalize to other scenes as well, whereas nerves particularly just take one input of a scene and work with that particular scene itself. So this was it for SRNs. SRNs mainly use something known as an LSTM model, which helps in a ray marching algorithm. Another solution involves LLFF to the view synthesis problem. LLFF refers to local light field fusion models. And so SRNs and LLFF were two particular solutions to the problem of view synthesis. Uh, now, oh, right. Um, Right. So now I'll talk about the methods that are used in nerves. First, we can try and understand what exactly a neural network is. So there is an example of a perceptron which takes in m inputs and m weights, and it approximates the value of uh, y hat with the help of this function that is shown here, which is the summation from I equals 1 to m xi wi. So this is used in order to approximate the value of y hat, and there's a neural network. So there is a feed-forward neural network in which each node in the input layer is connected to all the other nodes in this case. So this node is connected to all four of them. This node is also connected to all four of these, and this node is also connected to all four of these. So this was a brief introduction to neural networks, which are the basic architecture in the case of nerves. Uh, So we could try and understand what exactly a radiance field is, because nerves refer to neural radiance fields. So a radiance field is a function which takes in 5 coordinates and returns the density and RGB value at that particular position. So as you can see here, the 3D coordinates of the point are one of the inputs, and the other input is the view direction or the camera angle. These can be denoted using theta and phi, where theta denotes the angle from the z-axis and phi denotes the angle on the xy plane. These correspond to the azimuthal azimuthal coordinates in the azimuthal values in the spherical coordinates. We mainly care about using spherical coordinates because we are interested in the direction of the camera itself and not the exact location of the camera. So that's why we don't use Cartesian coordinates. This is a way in which we can transform Cartesian coordinates to spherical coordinates. Uh, this follows from basic facts in geometry. So we just use x is equal to rho cos phi, cos theta sine phi, y equals rho sine theta sine phi, and z equals rho cos phi to convert from Cartesian to spherical coordinates. Um, so uh, these are some scenes which have been generated by neural radiance fields, and these are mainly for non-Lambertian materials. So non-Lambertian materials mainly stand for materials which do not equally reflect light in all directions, compared to Lambertian materials which reflect light in all directions equally. Nerves can also insert virtual objects into real-world scenes, as can be seen in this case. So virtual objects can be integrated into real-world scenes in such a way such that the virtual objects behave just the way they would interact in the real world. So, so these two were examples of scenes that were generated by nerves. Uh, Now we'll talk about the concept of volume rendering, which is also used by nerves in order to generate images of a particular scene. So, as I said, nerves output RGB values and the volume density. So after we have these outputs, we need to understand how we are going to generate or render the image. So we rendered the image using this integral starting from Tn and going all the way to Tf. T of t, sigma of r of t, c of rt comma d and dt, where dt is the exponential of the integral from negative integral Tn to T sigma of R of S ds. Sigma of x denotes the color density at the position x. C of R is the expected color of the ray R. And T of T denotes the accumulated transmittance along the ray from Tn to T. So the accumulated transmittance is the probability that the ray has not yet hit a point before it encounters the point itself. And so now I'll talk about how we can how we can get the transmittance from the value of sigma of x. So there is an example that involves the calculation of the transmittance from the value sigma of x. So since sigma of x is the volume density at a point, it stands for the differential probability that the ray will hit the point itself. So between the time span of t plus dt and t, if the ray does not hit any, so the probability that the ray will hit a point is 1 minus dt times sigma of t. And so we can say that t of t plus dt equals t of t times 1 minus dt times sigma of t. After that, we just do some simple math in order for us to get the value of the transmittance from the point A to the all the way to the point B. And we can finally get this as the exponential of the negative integral from A to B sigma of t dt. This graph shows the dependence of transmittance and distance on the basis of the values of sigma. As the value of sigma increases, the transmittance decreases across for the same distance. So for sigma A equals 0.1, it is higher than 0.5 and higher than 1. Now our goal is to try and approximate this integral. In order for us to approximate this integral, we can use two methods. One is known as deterministic quadrature, and another is known as stratified sampling. So deterministic quadrature involves something known as Gaussian deterministic quadrature, which will involve using intervals, which will involve weights and points selected from those intervals. So we can approximate it using this formula where Wi is equal to 2 over 1 minus xi squared times Pn prime of xi the whole squared. And using this, we can generate the points xi itself with these particular weights. And this would help us approximate the area under this entire integral to help us get this value. Another method for approximating the integral is known as stratified sampling. In the case of stratified sampling, we partition Tn and Tf into n equal intervals, and we sample from each of these intervals. So after we sample a point from this particular interval, we can put it back into this equation. And now we get a discrete version of this integral. The discrete version of this integral is much easier to compute than this integral itself, because this integral could be working in much higher dimensions and can often involve tougher calculations. So I'd like to give an example in which we apply stratified sampling. So this is an example of a stratified sampling approach. So we first divide 0, 1 into 4 subintervals. So they would be split from 0 to 0.25, 0.25 to 0.5, 0.5, and so on. After that, we get a particular point in each interval, and we evaluate the value of the function at each particular point. And finally, we take the weighted average across all of these points in order for us to get the value of the integral. So this was how we apply stratified sampling in this case. So this denotes how the radiance field depends on the view of depends on the camera view for a particular image. So as you can see here, yeah, as you can see here, this is one for one particular view in which this is the water and this is the ship side, and this is for another particular view. And this third image denotes the radial distribution of the various color levels across the scene. So this denotes how the value of RGB and the volume density depends on the particular view. Now I'll let Shivesh continue the rest of the presentation.
Yeah, if you guys have any questions. We also have pieces in the back, so the future is that. Okay, I'll continue with the rest of the presentation then. Um, so what we have done so far is not really enough for being state of the art yet. We need to make some more optimizations by using some other tricks. So let's talk about them. The first of which we use is positional encoding. So the issue here is that neural networks perform poorly on high frequency variations, especially in color and geometry. So one possible solution to this is using the inputs and mapping them to a higher dimensional space and using these frequencies as input to the neural network instead of the lower ones. And this was actually established in a pretty old paper by Mira, where they showed that even if in the training data we have points of lower frequency as well as higher frequency, the model will still try to learn the values of lower frequency first and kind of spend more time on them. Uh, so this was one of the main issues we encountered here. So the what they came up with was they came up with this gamma function, which is basically a positional encoding function, and they kind of merged it with the existing network, and they were able to update the network to this new function over here. Um, Now, visually, what this you can think of this gamma function as basically taking some number between 0 to 1, like the original input here, and then transforming it into a three-dimensional or 10-dimensional vector, which has different values at each point. So now you don't just have lower frequency values like 0.1, 0.2. Now even the value which was 0.1 before has like four different aspects to it, and all of those might have a higher value or a lower value depending on the position itself. And this idea is similar to the one used in transformers, but the only difference being that there they were used to signify position in a way. But here we don't use them for position. We are just trying to map the inputs to a higher dimensional plane. Yep. Um, yeah, I think in the future works there has been a lot of work in the positional encoding. We'll even see some more variations when I talk about the future work. But yeah, I think that would be a good idea to kind of improve the position encoding to get more clearer images. It does. It does. Yes. Then moving on to the second trick, which is the hierarchical volume sampling. So like Vedant talked about it, basically what we do is we pass a ray through the image, and then we break the ray into n different sides and take 1 point each, 1 point from each of those sections. But what this does is uh, an actual image will have a lot of free space as well as a lot of occlusion, whereas we are only interested in the colors which we can view from that particular angle. So a lot of the compute is wasted on calculating for points which are not even near the object. So which is why now what we do is we try to find a probability distribution of where along the ray are the objects most likely to lie. And then we use a second neural network, which is the fine neural network, to try to sample the points in a way where we are able to sample points concentrated around the places where we expect the object to be. Um, and the way we do this is we basically take a weighted sum. We first train a coarse network, which is trained in the same way as Vedant described. And then using the outputs from that, we train a second network, which is known as the fine network. So for this, what we do is we take the outputs from the coarse network, we sum them up in a weighted average, and we fit a t distribution to it. And once we do that, we are able to break the graph into these sort of rectangles, where each rectangle which has a higher height in a way is able to describe that there is more likelihood of an object being over here. And then once we have this, we are able to sample more points along this part, let's say, as compared to this part for the second fine network. Here is a bit more of a visual explanation. So we have this ray which we pass to the object, and these white points over here represent the points used by the coarse network, which we then use to model a probability distribution. And then we use this to model these orange points for the fine network, which you can see are more concentrated towards places where we expect the object to be as compared to places outside of it or blank space or occluded objects. Um, Now let's talk about some more implementation details. So the loss over here is basically just a squared error loss between the rendered and true pixels for both the coarse as well as fine renderings. Um, and the way we get this ground truth is basically we have something known as uh, uh, SFR algorithms, basically a call map algorithm, which kind of gives a rough estimate of these ground truths, which we can use to train our model over here. And since we have like two different models, which is the coarse as well as the fine, and we need to train a new model for each of the renders, which is why this is kind of a different problem from other standard diffusion or other computer vision problems, where we need to train a new model for every render. Some more details. So they use a batch size of 4096. They use 64 points in the coarse network and 128 points in the fine network. They use the Adam optimizer, and the optimization for a particular scene takes about 200k iterations to converge on a single NVIDIA V100 GPU, and it takes about 1 to 2 days, which is a lot, especially for 2020. Um, and yeah, the results are obviously much better than the SRN and LLFF models previously. You can see that. No, this is just a normal. This is not the real plot. So the metrics are better, but let's actually go to their website and try to see some more results. Yeah, so you saw this video before, and then they have also posted some more examples of the view dependent appearance, where you can see that um, changing the view actually changes the render as well. So just by querying the view direction, they are able to change the lighting conditions. It's also evident from this example as well, where you can see the lighting conditions change. They were also able to use it for geometry reconstruction. Um, and this was the fitting real objects into the scene. As well as 360 where we capture. Yep. Yep. Yeah, I think that's how it works. But like this is not an application of this work itself. I think there were some other future works which were able to do this. They extended the nerves, but yeah, this was made possible because of nerves. Yeah, 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 yeah. Yeah, so these were some of the results we obtained. Now let's talk about some of the limitations as well as improvements made, because 4 years is a long time, especially in computer vision. So some of the problems which the original model had were aliasing and blurriness problems. So what that means is if you look at this line, um, it's kind of pixelated, and you can see that the points are not really blending in, and this happens because the pixels are generated in this manner. Um, but if you look at this line over here, it looks it looks much smoother, and that is because they have incorporated this blurriness over here to kind of better model the slanting architecture, slanting line. So this is one issue which we encountered, which is expected because we are using one ray to kind of render one point. So it is expected that we would obtain more sharp or drastic changes like this one over here as compared to this one. Some other issues were memory. It requires a lot of memory, and it also requires 2 days to train and optimize, which is a lot. Um, then there was also a large requirement of data set where we needed at least 50 to 100 images of each scene to be able to render images which were good enough. Now, some of these most of these problems are already there has been a lot of work on these problems, and they're pretty much solved now. So let's take a look at some of the models that solve these problems. The first of which is MIPNERF, which address the aliasing and blurriness issues. So what they were able to do is instead of using just one ray, what we want to do is we want to obtain information from the points around it as well. One naive solution would be, you would say that let's send multiple rays around this point and kind of merge the outputs. But the issue over here is that passing each ray takes like hundreds of iterations of the neural network, which we don't really want to do it for like 10 different rays. So what they came up with was they modified the, let me go to their website. Probably just see it there. So they were able to modify the positional encoding to change from a spatial one to a spatial region one, where now the encodings are actually able to capture some more information about the points around it as well. And what this does essentially is that now instead of when we pass a particular ray, we are not just passing a ray. Instead, we end up passing kind of a column, kind of a cone like this, from which we are able to get a lot more information about the region. And then when we are able to combine the results from that region, we are able to get points which are not as blurred and also not as aliasing as before. Maybe we can take a look at some of the results. So these are from the NeRF models. This one is from the NeRF, and this one is from the MIP NeRF. And you can see that when we zoom in, there's a lot of blurriness and aliasing issues over here, which were resolved by MIP NeRF. And as well as some more, you can see that MIP NeRF is able to capture much more sharp features um, in much higher quality. Then another improvement was made by NVIDIA when they released Instant NGP. So now, originally, nerves were taking, like I said, 1 to 2 days in optimizing. But NVIDIA, in this paper, they really changed the game where, once again, just using a single GPU, which was the RTX 4090, they were able to train the nerve within a minute, is what they are claiming. Um, we can take a look at some of their results as well. So you can see that they're actually quoting the elapsed training time over here. And you can see that even in like 10 seconds, it's a pretty good render. And they even solved some other problems such as the gigapixel image. So it's training in real time, and when it's zooming in, you kind of don't even realize that as it is zooming in, it is training at the same time. So really impressive work over here. Um, much faster training. So all of these you can see are trained in less than 10 seconds. Another improvement I'll talk about is pixel nerf, which solved the problem of using multiple different images. So, like I said, the original nerf paper required about 50 to 100 images, but the pixel nerf is able to do the same, pretty similar job in much less images. Like they claim to do it in just 4 to 5 images. So, if you see here, these are the two input views. So when you're given just two inputs, uh, this is what Pixel Nerf is able to produce. Meanwhile, this is what Nerf gives when you just pass in three images. And this is for Pixel Nerf. So you can see that they were able to resolve a lot of the noise and reconstruction effects which were previously encountered in Nerf. Then since then, there have also been some more works such as mobile nerf and nerfies. So mobile nerf was able to solve the problem of uh, using a large scale GPUs again, where they were able to run the nerf renderings on a mobile phone, on an iPhone 10s. And you can see the results also. It's not too bad. I mean, not as good as the ones trained on the GPU, but still pretty good for the ones trained on a phone. Another interesting one was Nerfies, um, where they just take selfie videos and they're able to turn it from using just the phone. They're able to turn it into free viewpoint portraits, such as these ones. It was also used in art. The NVIDIA has an instant nerf art gallery. Then we also have Mega Nerf, which was used to train nerves on a much larger scale, such as this like basically an entire stretch of road, which was not possible using prior models. So a lot of improvements on nerf has been done, and I guess it is kind of the standard one used in 3D reconstruction nowadays. A lot of researchers are working even at U of T. You'll find a lot of labs working on this. Um, yeah, that's about it from our side. You can find these slides on our GitHub. Thanks a lot for attending the event, and hope to see you in our next one. You can follow us on social media using this QR code.